Hello everyone, I'm Kohei Itoh from Keio University, Japan. Today, it is my great pleasure to introduce quantum computing in Japan as a program director for the Quantum Information Technology MEXT Quantum Leap project, which is run by the Japanese government. Current global trend in quantum technology development is quite clear. Many countries place quantum technology as a key technology. Governments and private sectors are increasing related budgets for R&D, establishing core research centers, and developing human resources strategically. As you can see, US, EU, and China are the big three pushing the research on quantum technology with large-scale budgets listed here. And those listed are, I think, only partial list. An entire list is quite difficult even for us to figure out. In the case of Japan, this year, Japan has actually put in about 209 million US dollars for the quantum technology. And one is the Quantum League flagship program that I'm responsible for. And this is run by Ministry of Education, Culture, Sports, Science and Technology. Abbreviation is MEXT. There is also a Mirai project that Japan Science Technology Agency, this is also the agency run by MEXT, is running a quantum technology project. Innovative AI chip and next generation computer technology development project is going on with the New Energy and Industrial Technology Development Organization known as NEDO. And R&D and quantum cryptography in satellite communication is being pursued by Ministry of Internal Affairs and Communication. And opto-quantum basic technology is being pursued by Cross-Ministerial Strategic Innovation Program, SIP. And finally, Moonshot. This is a long shot research, and this is run by, again, JST. As I said, quantum technology is recognized as important core technology actually in the 5th Science and Technology Basic Plan. And this plan was approved by Cabinet in January 2016, and we are in the process of making the 6th one, the next one. Maintain and improve world competitiveness in photonics and quantum technology, specified in Integrated Innovation Strategy that was actually published in June 2018. So many ministries lead R&D projects on quantum technology. As I explained to you in the previous slide, MEXT, Ministry of Education, Culture, Science, Ministry of Internal Affairs and Communication, Cabinet Office, and Ministry of Commerce, Economy, are all running a different kind of projects. And the goal is the promotion of the state-of-the-art research and industrial innovation. And as Japan has been leading the quantum technology, as you can see here, in 1998, Professor Nishimori of Tokyo Institute of Technology invented the concept of quantum annealing, which led to industrialization of quantum annealing technology. And also in 1999, Yasu Nakamura and Jason Tsai, back then at NEC, now professor at University of Tokyo and professor at Tokyo University of Science and Technology, they actually invented and demonstrated the world's first solid-state quantum bit. And this has led to development of large-scale superconducting chips that are being developed by IBM, Google, Rigetti, etc. So we want to be the forerunner. Japan wants to be the forerunner in the state-of-the-art research, and also in a way, actually in the action of making turning those basic research results into industrial applications. The framework and process was actually put together by Chief Cabinet Secretary at during the Integrated Innovation Strategy Committee in last December, and Chief Cabinet Secretary commanded to study for formulating strategy by setting an advisory board on quantum technology. So the advisory board was established, and these are the members of the advisory board, and that includes myself here, and task force are being established within different ministries, and after a number of intense meetings, last January, actually this year's January 2020, the final report was summarized. And the current quantum technology policy, research policy, and also projects are established based on this report. So the basic policy and visions for the society are the following. We put quantum technology as an innovative technology that holds a key to exponential, discontinuous, disrupted development of our economy and society. And government establishes technology platforms and transfers them to the wide range of challenges and sustainable growth and developments. And this concept of quantum technology and innovation is carried out with strategic efforts as a national commitments. So not only quantum technology, but also combination and comprehensive promotion of quantum technology and existing classical technology is being pursued. For example, Fujitsu is working on digital annealer. Hitachi is working on so-called CMOS annealer, and Toshiba is working on stimulated distributed algorithm. And these three representing technologies that Japanese companies are pushing actually are the semi-quantum, also, I should say, not exactly quantum, but quantum is inspired technology that in which quantum algorithms are simulated using silicon chips, and such calculation actually turns out to be faster than the same job performed by using classical algorithm by silicon classical computers. And of course, integration and reinforced collaboration with quantum technology, with AI and biostrategy is very important. So at the end, we want to realize productivity revolutions, health and longevity, and increase the safety and security of the society using quantum technology. Innovation that are expected to emerge from our effort includes, of course, new products and service by big-scale computation, early detection of cancer, brain disorder, or any health markers, and so on. Quick evaluation of medical medicine through quantum effects. So it's more of the pharmaceutical efforts as well. Quantum sensors are expected to participate in wide variety of social goods, and quantum cryptography will assure secure internet by quantum cryptography. And of course, we are also interested in so-called quantum materials emerging materials with unique properties based on quantum law or quantum mechanics. So quantum technology, we believe, will bring solutions to many social problems, and quantum technology will increase our industrial competitiveness. So some of the summary of the quantum technology include identification of priority areas to accelerate innovation, quantum computing, quantum communication, quantum internet, quantum cryptography, and so on. And also, we have formulated detailed technology roadmap and integrated area roadmap to guide Japanese scientists and engineers, uh, uh, basically to encourage them to enter this exciting field. We are also establishing many quantum hubs, basically research centers, software hubs, hardware hubs, sensor hub, and so on. And also we are establishing many international collaborations. So Japan, US, EU multilateral symposium was held in December 2019, and there number of actually agreements were signed between those three parties. 5 pillars towards an achievement of quantum technology and innovation includes technology development, international collaboration, industrialization and innovation, intellectual property and international standardization, and human resource development. So now I move on to description of each project. MEXT Quantum Leap project actually concentrate on computers, quantum computing and simulation, quantum metrology and sensing, and next generation laser that involves quantum technology. And I'm in charge of this quantum IT, quantum computer simulation part. So let me explain type of projects that we have within this quantum IT area. So within this quantum IT area, there are 2 flagship projects, one hardware, one software project. The flagship hardware project aims to build superconducting quantum computers. So the goals in a very simplified form are those number of qubits that we try to achieve in next 2 years, 5 years, and 10 years, and so on. However, of course, we want to build a quantum computer that has 100 qubits, that has sufficient computational capability, deploying all, leveraging all of those 100 qubits so that we can actually stay in the top group of superconducting, not only superconducting quantum computer, but quantum computing hardware community in general. Flagship project number 2 is so-called Quantum AI. So it's a software and architecture for a noisy integrated scale quantum computer. And application will take advantage of the quantum supremacy that the leader, Professor Fuji of Osaka University, is trying to achieve. And hopefully in 10 years, quantum AI for condensed matter physics, machine learning, and everything will be developed so that we will be serving such technology to our partner countries. Also within this quantum leap, quantum IT area, we have smaller 6 research and development teams basically centered around the flagship project. One is led by Professor Omori, working on attosecond coherent manipulations of cold atomic gas, which actually aims to perform quantum simulations of difficult problems. Dr. Mori leads a project on silicon quantum computer hardware developments. Professor Nemoto leads quantum software, actually midware integration. Professor Toyota of Osaka University leads ion trap quantum computer developments. Professor Fujii, already described in the previous page, Osaka University leads a project on quantum software. And also Professor Yamamoto of Keio University leads quantum software project. I forgot to mention in the previous page that the superconducting qubit project, flagship project, was led by Professor Yasu Nakamura, the same person who invented the first quantum bit, solid-state quantum bit in 1999, back then in NEC. Now Professor Nakamura is a professor at University of Tokyo and also a leading scientist at RIKEN. We've also inaugurated a Quantum Leap flagship project, educational course in quantum technologies. So again, Professor Nemoto leads a standard program for higher education center. Professor Ozeki of Tohoku University leads development of quantum natives through practical training. And Professor Noguchi of University of Tokyo develops the online courses and summer school program for quantum technology education. Apart from our QLEAP project, there is a separate program called Moonshot. And Moonshot established 7 goals, and among them, the goal number 6 is the realization of fault-tolerant universal quantum computer that will revolutionize economy, industry, and security by 2050. And basically, this is towards fault-tolerant universal quantum computing. And for this, we actually have a quantum network project, photon source detector, quantum memory, quantum interface technology. Of course, the core is a hardware development. And of course, the software development accompanies this hardware development for co-designing fault-tolerant quantum computing. And there are milestones at 2030 and 2040. It's a 10-year project from this year to 2030 to achieve this milestone. And then that will move on for 2040 and 2050. Finally, we are establishing many quantum technology innovation centers under guidance of different national institutes. You can just read this through and see that we are establishing many centers as hubs for international communities. One of the hubs or centers that I established at Keio University is so-called IBMQ Network Hub at Keio University. This was established in 2018, and at the beginning it was solely funded by 4 companies. We have 7 full-time faculty members dedicated to work on this quantum hub for algorithm and softwares. We have 7 research scientists working on them. We have scientists from 4 plus now 2, total of 6 companies. And also we have 4 member researchers staying from IBM full-time at Keio University. And of course, we have 20 plus students working together with all these PhDs. So it's a big project, big operation. And we're pushing quantum finance, uh, finance research for verification by simulator and IBMQ machine. Quantum chemical team is pushing chemistry related project. Quantum AI team is pushing high accuracy data classification and other machine learning using IBMQ machines. And there's a system team that actually develops the basics of computer scientific aspect of middleware and so on. So this is a list of selected publications by KOQ Hub. This is the last slide, and hopefully you're convinced that Japan is very serious about development of quantum technology, and we will be hopefully serving as the core members for the development of the next generation of quantum technologies. Thank you very much for listening.